Okay. So essentially, yes, we have prepared some slides, not too many. So I'm senior lecturer of software engineering here in Queen's University, and we'll just give you a bit of experience from our past projects in scientific software development. So kind of to tell you a bit about my background and myself. So I'm kind of a very international person. I've lived in 5 countries, as you can see there. So very international. I lived in Canada for many years. I did my master's and PhD in Canada, all in software engineering. So I guess, as you can imagine, so I think in this nice group, we have people from different areas of science and software engineers, which we want to collaborate to develop higher quality software at the end of the day for scientific purposes. And in terms of work experience, I worked here in Canada, Turkey, Netherlands, and now in the UK. Okay, we'll go to Dave. Would you like to mention your background?
Sure, thanks, Vahid. So hello, everyone. I'm Dave Cutting. I'm also a lecturer at Queen's. Less impressive work history and research history than Vahid has done, but my sort of academic research has been around software engineering. But since sort of taking that on, one of the things I've ended up doing is more and more consultancy work. And what's been interesting over the last few years, or the last sort of 5-6 years, is that I've ended up actually doing less and less coding, to the point where someone said, well, what is it you actually do? And I describe myself in my consultancy as a software midwife, in that I get involved in the delivery of systems. Certainly not involved in the conception of it. Individual companies, come up with that, and once it's delivered, that carries on. But I spend a lot of my time helping companies kind of work with developers to actually realize an image, and obviously sustainability then is key. So I'll try to cross that over into the scientific side. Thanks, Pete.
Many thanks, Dave. So in terms of, so we'll try to essentially give a presentation for about 35 minutes to 40 minutes, and of course, please interrupt us in the middle, because it would be nice even to make this more interactive, because it's not too formal. So I'll talk about one of the projects that I was involved in, and then Dave has 2 projects there. Sorry, and then I'll also just give a very brief overview of the research literature in the area of, we actually did a systematic mapping study, like a systematic literature review in this area. So, okay, the project I want to talk about is, I actually received some good grant in Canada about 10 years ago to develop a software for oil pipelines. And then we had different scientists from different areas to work on this. So I'll talk a bit about it. I'll talk, perhaps I'll mention just a tiny detail about the technical aspects of that software, and then more actually on how different team members from different areas of science work together, and what was so what kind of challenges we observed, and what kind of essentially steps we took to do a good job in that project. So in terms of the context, essentially, so the context is that, yes, as you can see here, we're dealing with oil pipelines. So the challenge is really is that the pumping costs of oil products across pipelines are enormous. And the worldwide total of these pumping operations are several $billion per year. This is a map of North America, but similar one. So it's in Asia and Europe and all over the world. We were focusing at the North American, the Canadian and American pipeline system. For example, each of the pumping stations could consume as much as $2 million a month. So this is enormous. So really the whole thing, so in terms of inception, the idea was that, I was approached with a few people, they said, well, so we kind of said, there were industry partners and academic partners. And then we wrote a research grant to the Government of Alberta in Canada And then we were successful to get about $300,000 for a duration of 5 years. In terms of the team, of course, you have the different types of engineers, slash scientists, civil engineers, mechanical and chemical engineers. Myself and my team, we were the core software engineering team. And and I have put a picture of myself and my team here, that we work together. So the two companies here on the right-hand side, Enbridge and Pembina, they were the kind of the actual oil pipeline companies. They had the domain expertise. We were working with, collaborating with an optimization and civil engineering company to get the expertise in that area. So it was kind of, I would say that it was truly multidisciplinary in that you had different types of engineers and scientists. And the goal was to develop, for an optimization software, a software would interact with, and so I will provide a very little detail of that. Again, very high level, 2-3 slides. So here I'm just showing the final product. So kind of a Windows application was developed. There's a demo video of that in YouTube. So in simple terms, user interface was just showing, you could, of course, draw different pipelines in another software and then feed it to this tool. It will show it, and you can click on each station to get more information. The actual use case was just to optimize. You just click the button, it will optimize and show you the configuration and the speed, so what speed should be used for each pumping station so that the overall cost consumption is optimized. We were using we used a variety of optimization algorithms, which for those of you who may be interested in linear programming, mixed integer linear programming, genetic algorithms, and etc. Again, I'm sure for those of folks who are very keen on math and optimization, we find that aspect interesting. So again, very high level, what kind of software it was, and then I'm going to mention this and then come back to actually the sustainability and then what kind of software engineering challenges we observed in which different scientists were working together in this project. So it was a software that had to work with the company's control systems and SCADA systems, as they're calling, supervisory control and data acquisition. So we had to have interoperability with those other systems to get gather data and then post the data. There was an optimization engine we were using called Lindo, and then Google Earth for showing the map. Several best practices we were used, such as in terms of software architecture, model view controller. I think some of you may be familiar with that, MVC. So it was kind of, let's say, it was actually an action research, let's say, that we were seeing the challenges and then we were finding out the best way to deal with those challenges. So again, a little bit about how much software we developed. Of course, line of code is just showing the actual thing, but of course there was lots of effort behind that. So some C# code was developed for the whole application, and then there was also some for optimization aspect of it, some about 9 kiloline of code of domain-specific language in that particular software that's just for optimization. So you have optimization and then the user interface part aspect. Okay, now it's really, I think this is perhaps most relevant for what we are, I think we have gathered today and in this event. So we experienced lots of interesting things, and then we learned few things, and then we had some challenges. Just like any interdisciplinary team, few things went well, few things were challenging, but we made the most out of it. And actually, can say, without praising ourselves, it was a good experience and was successful at the end. Because we were able to commercialize the software, we published a few papers, students did masters and PhDs and graduates, and the industry partners were happy. So I think those were signs of good signs. So some of the challenges was that I think these are also typical mentioned in other parts of the literature, and I can see in other places mentioned. For example, some challenge was that the terminology used by conventional scientists and software engineers were different, right? I mean, I ended up learning a tiny bit of, you know, the oil and pipeline terminology, you know, the head, pressure, you know, the pipelines, you know, the because my area is not chemical engineering and chemistry, so but we ended up learning a bit of each other's areas. We were using different terminologies. We're telling them, you know, like, let's gather software requirements. You know, for chemical engineers, this wasn't clear. You know, what is software requirement? And then we found that there's a need from both sides to learn from each other. So really, we were even thinking, yeah, if the software system was to be developed by one side of this group, perhaps we did a good job because we put all the knowledge together and developed a good system. But yeah. And initially, conventional scientists, like the scientists outside our team, thought software engineering is just coding, and we had to tell them, well, it's not just coding. We have to test properly. We have to design the system properly. So these were kind of the interesting things that we learned. And then we have actually a technical report out of the book as well, which appears on our archive website. And some of the other questions that we were, any questions so far? I hope I should stop and then ask if anybody has any questions so far. Seems none. Okay. And so these are some of, I like to ask questions. So we kept asking ourselves questions along the way, to proactively do the right work and take the right course of action for any activity that we were doing. So going back to classical software development lifecycle, I mean, not just in terms of cliche, but in the actual sense of doing these things. I mean, because it was a, again, project that we had other types of scientists, we had to make sure that, we would get all the requirements as much as possible, although we could not, because things would emerge in an iterative fashion. How to design the system so that it can integrate with other systems. You have to get to know other systems, to get to what are the interfaces, so etc. How could we write the code to ensure high maintenance and understandability? Because this thing was going to be, actually we kept updating the system in 2015. So yeah, the system lived for a few years on, and then we passed it through commercialization effort to a few companies. And in terms of testing, I mean, testing optimization software is not easy. So for those of you who are familiar, how can we really know that, I mean, the optimal results are provided by this software are really optimal? There are a few heuristics, so we applied them, such as sensitivity analysis and etc. Yeah. So, and I think as software sustainability, again, is like, again, the classical terminology is really about the maintenance. How do we write the software so that, it's, in terms of design technical debt, that it could maintain it? Because we actually, after a few years, I got other team members who had to work on the code base. So they had to understand it in a reasonable time. So we really have to apply, any types of design patterns and best practice to make sure that the code is going to be readable, because it's, especially the optimization part of it, it was quite sophisticated code. Now kind of taking one step or two steps back. So I think now that's the end of that project, but I thought also to have one or two slides just while we were doing this project, we were aware that there's lots of literature published elsewhere in this area. So we actually, for example, if we go to Google Scholar and just, put development of scientific software with different terminologies, I mean, yeah, this one is showing 162,000 hits, and let's say, so lots of, I'm sure in your areas, perhaps you also have seen lots of this kind of papers. For example, the number 2 in this list is an interesting title: scientific software development is not an oxymoron. So the first one actually, the first one seems to be a paper in computational biology. I mean, it has been cited about 10,000 times. So we see that and then dealing with risk in scientific software development, 10 simple rules, so etc., etc. So what in year 2010 that we were doing this study, we gathered about 130 papers. So to the systematic literature review guidelines. This is the picture of three of my very nice colleagues at that time that we did this study with. So we published it. So what we showed was we kind of classified the papers. For example, we classified them by domain, frequency of scientific disciplines. For example, physics was there were more than 30 papers from the field of physics who had published in this area, those papers. Math, biology, HPC, general, engineering, chemistry, biomedical, etc., geoscience, and medical. And then we provided the reference of them so that anybody who wants to have a look at these things. So the whole paper was like a reference or index to those studies. We also classified them by programming languages. Somebody was saying, we developed a software in Fortran, for example, for physics. They were sharing their experiences. This is kind of the classification by the frequency. We also looked at essentially the software engineering areas by the so-called software engineering body of knowledge, SWIBOK. Requirements, design, development, testing, maintenance, configuration management, agile, and performance. So in different papers, we're looking at the whole thing from different angles. Then they're sharing experiences in most cases. Yes, so that's my part. I hope I didn't go too fast. So yeah, okay, so I now hand over to Dave.
Okay, brilliant. Thank you very much. I'm going to try now and share my screen. Hang on. Oh, this will show up others. See if I can work with technology. Hey, desktop 2, my many monitors. Let's give that a go. Right, so hopefully everyone can see that. Zoom has gone a little bit.
Yes, you can see it.
Crazy. All right, so I'm just going to start off. Just to echo what Vahid said, if anyone's got any kind of questions, please feel free to jump in as I go along. I can't see the chat anymore, but just jump in on the audio slide. In person, I think we both intended to make this more of an interactive workshop, but having gone online recently and experienced the wonder of digital tumbleweeds as opposed to physical tumbleweeds, I've made it more of a kind of a talk at you. But please obviously do kind of jump in if there's anything to say, and at the end we'll have some time for questions, answers, and also any interesting collaborations we're looking to do. So what I really wanted to talk about was my experience on a couple of projects that I'd done in terms of academia, and really how that is different to how I've worked in industry. And what I found, this is myself. All of these things I say, people do this. What I mean is that I do this, and maybe some other people do it as well. Is I found that I would often end up describing things as research software. Now, what I meant when I said to you, oh, I can give you access, but it's research software, was not it's wonderful Nobel Prize winning software. What I meant was that it was a pile of crap, basically. It meant that I'd written it, very flaky. It was usually unfinished. It was incredibly delicate. It ran on my laptop on a Thursday if the winds were aligned and the network shares were in the right place. Utterly undocumented. And what I was basically doing was limiting my liability. I was kind of saying, don't come to me if there's a problem. And also, please don't judge me. Don't ever judge me by this code, because it was always quick and dirty. And what I actually meant really was this is a very poor piece of software. It's not research software. It is just a very, very poor piece of software, I'd put. And as I'm sure we all know, any software grows, is subject to growth, is subject to organic growth. Over time, new things come. And of course, to quote sort of, famous people in the field, the more successful a piece of software is, the more it will be subject to growth and it will be subject to change. And while controlled growth, kind of planned, process-based organic growth is absolutely fine, what I found was that in the majority of research groups that I've been involved with, research groups that develop software, the growth has been organic, but it's been uncontrolled. So the software has grown, and I use the term like a tumor. It was in bioinformatics team I was working with when this first came out. So it was all sort of cancer metaphors. And this thing grew and grew. You know, you start off with a relatively simple tool, and by making very quick decisions as requirements come up, things change. And my first experience really of this, and the barrier this had, was during my PhD. So I was doing a PhD in software engineering, and you might think that if you're doing a degree in software engineering, you would use software engineering principles. But if any of you ever visited an electrician in their house, I'm sure you know that electricians are the people that have lights hanging usually out of the walls. And software engineers are, I think, probably the worst people to write their own software. So I was developing this JCRA, Java Code Relationship Analysis, core sort of fundamental piece for our research group and a core piece of my research. And I started it as a 10-line thing that then grew as a proof of concept. And I added more and more layers to the onion, more and more layers to the tumor, to the point where it became incredibly unsustainable. So not only could I not add anything to it, but someone came along and said, oh, yeah, really good, we like the output from that tool. Could we please include it in our workbench? Could we plug it into our group workbench? And the idea, you know, filled me with dread, because I was almost embarrassed to show people how it operated. It worked in a variety of different ways. It wasn't well thought out, and it wasn't done. And this forced me then to go back to square one, stop all actual other productive work for, I said 2 weeks there, I actually think it was a month, and do nothing but rewrite this thing from scratch using documentation, proper architecture, that kind of thing. And what that investment showed to me was, one, that software lived with me for the rest of my career in that group. Two, we could immediately make it available as a plugin. Three, I was less embarrassed about kind of handing it on to other people. So that was my experience with that project, is that for all the right reasons, I ended up with a horrible bit of software that we needed to put together. And this kind of got me thinking really about the fallacies of research software. So again, I'm using this kind of term research software as I use it as a descriptor, the lies that I tell myself when I was writing research software. And these are quite common. So I think, you know, I'll be the only person to use this. I'm writing a piece of software, I'm going to do it. There's no point in documenting it, because I'm the only person that's going to use this, and even I am only going to use it for 3 months, so I'll never need to come back to it. It's just a proof of concept. Quite often in academia, we're looking to chase the next grant, we're looking to prove something, we're looking to generate an output now because there's a paper deadline next week. The software is just a proof of concept. I can tell, oh, it doesn't matter, right? I'll just write it, just a proof of concept. What I tell myself all the time, I'll come back and I'll do this properly later. The amount of my code, which includes things like comment, to do, fix this, is shocking. I think nowadays there's less of it. I obviously eat my own dog food nowadays, but I go back to code that I wrote, which still runs in production, which was written kind of for 20 years ago, and it's full of to do, fix this, to do this properly. So we tell ourselves lies, you know, I will come back and I will do this properly later on. And of course, the other one is that, yeah, all right, this time, no, there's no point. I'm going to carry on. I'll do it hacky this time. But wistfully gazing into the distance, next time I'm going to do it properly, and I'm going to go on. And this all kind of stems, I think, from one of the fundamental things that underpins all of this, that we think the software is not the product, it's just a bump in the road. No matter what field you're in, we're writing software, but the software is not the output. The research is the output, the findings are the output, the graph that goes in the paper that gets published is the output. The software is not the product. Now, what became clear to me was that while I had this mindset on one half of my mind to do research, on the other time, I'm doing a lot of consultancy with private business, and it's a very different thing there. And I was saying very, very different things there than I was to myself in research. So in industry, we always focus on the longevity of the software. It's all about the return on investment. The key here is investment. The creation of the software is viewed as an investment. There's a dollar value put on it. There's time, there's effort, director time, designer time, things actually being spent out of someone's actual wallet rather than a research grant. So obviously, industry is always interested in, well, when is it going to pay for itself, and how long is it going to keep paying us after that to return the investment that we've put into it? And that longevity in the investment means that they also consider maintenance, they consider resilience, so sustainability, if you like. And these are key factors. And I would sit in meetings where I was helping out with, the project management, this software midwifery, as I say it, and I would be helping companies make arrangements with software development houses. And I'd be the one asking, well, hang on, who has the code? Who's going to have it? Is it going to be technically documented? We need to put requirements in the contract that they will provide certain things so that we have long-term sustainability of the software, that you own it, you've invested in it. If that company goes bust, you fall out with them, it doesn't matter. You can get another developer to come in. And the key thing, and I felt the difference between all of my research practice to that date and all of my industry practice, is control. All of the industry projects I worked on, I emphasized control, control, control. Let's control the growth. Let's have an identified change process. Let's have plans. If we're going to use Agile, that's fine, but let's control it. Let's document it. Control is key to what actually happened. So skip forward a few years, and by this point I'd finished my PhD and moved on, and I was working at the Tyndall Centre for Climate Change Research as a senior research associate. And my job was to write some software in order to do this particular project. Silex, a scientific library that then became another product that we're using later on. Now, this was a proof of concept. It is research software. So research software, I would say, is one where you don't know whether it's going to work or not. Very little in industry, you don't know whether the output's going to work or not. But we could plan the evolutions. We could do something like we would do in industry, where we look at what are the requirements, what are the initial requirements, what are the phases of implementation we're going to follow. Every step was documented. Documentation of code was important. I actually did it, hated doing it, I forced myself to. And I was working under the assumption, I forced every decision to be looked at with this sort of frame, that there's going to be longevity to it. Others are going to use it. This software will continue to live, and it will continue to return on the investment that we've put into it. And that shift in the mindset forced me to develop it as if I was developing it for a paying real industrial customer, rather than being paid a salary on a research grant. And the dividends actually amazingly paid off very, very quickly. So the dividends were directly to myself. It was amazing how quickly I wasn't kicking myself, because I find that when I develop quick and hacky software, within a week, I'm ruining the decisions that I made the week before. I'm wishing that I'd had a better data structure. I wish I'd done things properly. And I end up working more and more around the compromises that I made in the early days. So doing Silex properly as an industrial project with control processes and documentation meant it was great. I had a decomposed architecture. I'd used proper software engineering concepts. Now, this then skipped forward sort of roughly 12 months, and I got offered a faculty position at Queen's, which was marvellous, but it meant that I was leaving the project far earlier than I intended to do. So I had to hand my research software over to someone else. And this is where, for the first time in my life, in my research career, I was happy to actually open up the code base. I was happy to hand it over, because it was in a state where I could actually say, yes, you can use this and you can sustain it. I picked up, and I'm sure we all have, hundreds of, maybe not hundreds, but tens of projects where I've been involved and someone said, oh, we have this bit of software, could you just change it? You do computers, could you just change it? Things like weird Java applications to do word clouds of environmental terms and things like that. And I always hated the people that had wrote it with a passion, because they created this kind of legacy of awfulness. But I knew at the same time that most of the time I was doing exactly the same thing. But as I say, having done this properly, having focused on investment and longevity, I don't think it took that much more time. And certainly within a couple of weeks, within a couple of months on the project, I was reaping enough benefits that I was already reaping that investment that I put in. And as I say, when I eventually did turn it over, it didn't go what I call a loose bunch of bits, because some of the projects I've turned over, the kind of next person turns up and you go, here you go, here's a pile of code. None of it works, half of it's in Fortran, some of it's in Java, none of it compiles. Good luck, I'm leaving now in order to go. So that's my kind of key message and what I hope to get across, and the decisions that we we hope to take on. So as I say, I would have made this more interactive, but thank you for listening to me rabbit on. I'm sure if anyone has any questions, Vahid or I'll be happy to answer them.
Okay, so anybody have some questions for David and
Vahid?
Vahid, thank you.
I have a question. I'm not sure. This is the first session I've attended. I don't know if there's something I need to do to put my hand up, or do I just say?
Yeah, just go ahead and say.
So I enjoyed both of those talks very much. And David, you absolutely nailed it as far as I'm concerned. With you reap what you sow. Basically, the investment you put into your software engineering now will pay back many times in the future. And it's what we tell people and what we've been telling people for a decade now. However, evidencing that is the difficult bit. So really getting that point across to somebody who might be earlier on their software engineering journey is not always that straightforward. So how do you make that argument? How can you make that argument and really give it some impact when persuade somebody to do the work now so they'll benefit in the future?
I think I find that tremendously difficult. It's a very open question. I mean, the issue often is you need to allow people to realize the errors of their ways. I mean, I'd probably be a perfect candidate for someone who should have known better when I got into research. I'd been in industry, I'd then gone through, I'd done a master's, and I then started my PhD. I'd done software engineering, we'd done it, and I knew all of it. And as I say, I was off out consulting, yet I still made poor decisions in that. And I think you have to kind of learn that. I don't know is the answer. I wish I did. I don't know. I mean, I know Vahid has done a kind of look at some of the literature in this. I don't know if he can maybe speak to that on any ways of getting the message across and trying to quantify what the benefits would be.
Yes, yes, I think good point. Yeah, from the literature that we have seen and also my personal experience is that I kind of also agree with Dave that we let those let's say junior colleagues that are early in their scientific software engineering career just to make some tiny mistakes, and then they kind of learn, because at the end of the day humans like that, right? I mean, we of course to some extent we would listen to others' experience and evidences, but also human nature is that we end up making our own mistakes to actually believe it strongly. So, but my own experience in few occasions has been that to actually let's say, my master and PhD students kind of, let's say that early in the process, I said that, well, let's imagine, we hurry up and then do a patchwork. We just develop the software in a kind of ad hoc manner without some best practices. And then I said, well, if it continues like this, imagine if next year somebody else just like you, comes to the team, will he or she be able to understand your code? So trying to kind of create those scenarios. And of course, this is not always easy, but and of course, we can also, point our junior colleagues to all the experience papers that have been published in this area. And there are hundreds of papers, literally. But also having those friendly conversations and then trying to just transfer, the evidence which is, stored in each of our brains to other person to some extent, so as much as possible.
I'll just quickly add to that. I think one of the interesting things generally at the moment is the change in some of the paradigms that software development full stop is using. So the kind of, I appreciate it's not a very new thing, but a move towards, microservices, having things abstracted away, serverless computing, all these kind of things. And they do show concrete benefits. And my thesis, not yet necessarily borne out by evidence, is that engineering in that domain makes us better decomposed software engineers because we're writing interfaces rather than kind of horrible monoliths. So, hopefully that kind of thing will become almost a self-fulfilling prophecy in a way, as people like to do that.
Thank you.
So Someone has asked a question on the notes. Would you like to verbalize and directly ask Vahid and David?
Sure, that was me. Sorry, I'm going to switch my video on and remove the sticker. Sorry for that. So going back to the question or the statement that research software was signifying terrible code back in the day. The question would be, how do we get people to take claim of the software really early on in the project? But also, and I think this is due to the point I would like to make, is that lots of the answers are hidden in the command chain, so to speak, in research software development and engineering. How do we get our PIs and project leaders and funders, etc., to realize that it's really costly to make software sustainable from day one, if possible, or in iterations, but it's going to cost you. How are we going to convince people that this is a cost that we need to pay?
So if I could just come in on that, sure, maybe he can follow up, but I think it again, it's a very real problem. If you imagine that in industry, what we tend to do is we would actually have code reviews. People would sit down and look, and you would have some sort of quality metric there. Obviously, that really doesn't happen. What people do is they look at the outputs at the end of it, and you are perfectly correct, because the PIs are chasing that next paper deadline. They're not really interested in sustainable tool chains in the majority of things. One of the items that I think is quite interesting and would have potential on this is an increasing requirement for code to be open sourced or open. Open source is a particular license, but open at the end of projects. We're increasingly seeing a move towards open access for papers. I think we should see that for data, and I honestly believe that we should see that for code as well. And the idea being that if you present a finding, you must be able to produce enough artifacts to allow anyone else to reproduce that finding. It happens in other scientific disciplines, it doesn't happen with software. And we are seeing increasingly now that funding bodies are looking at, well, what's your output going to be? Okay, so it's going to be it's going to be a tool chain. It's beyond just a proof of concept finding. And I know, for example, Vahid are applying at the moment for a grant, and one of our outputs is specifically identified as open source software, which will fulfill the tool chain. And so I would hope that would, if that became more of a target. I don't know if Vahid has anything to add on that.
Yes, sure. May I also, yes. Actually, when I would like to convince, I think the question was that if other people or other stakeholders, if you want to convince them that investing or developing software in a more sustainable manner makes sense. We could provide some experience. I just want to give you a very short little example that I had. But when I used to work in Netherlands before coming to the UK, actually there was a large research center, and then I had the conversation with them. So the situation was that they were developing a software. It was the domain was bioinformatics. They have been developing a large software tool chain for many years, for more than 10 years. And actually they approached us. We were almost in the point of writing grant, but I moved and we couldn't write it. But the whole project goal was to refactor the software project. So the software had come to a point that was like that, like, don't touch it. Everybody was saying, don't touch it. It just works. If you want to add a feature, it will break. Unfortunately, this is the case for many. I'm not saying for all scientific software, but for many scientific software systems, because they have been built in a very, let's say, ad hoc or organic manner and without thinking for future maintainability. So really, those people who have seen those cases, or we could convince that such things exist, such cases exist, I'm sure they will be convinced. With some efforts, they will be convinced that, it makes sense. It's just the whole technical debt, and then, it's a whole conversation of that. You can write something, with a bad design such that it works, but then you say, well, let's think about it. Of course, if it's just for a little script for one paper, of course, you can get it to work and you just run it and then you throw away the code. But if it is, let's say, if somebody in a research discipline wants to have a piece of software that's going to be used for a few years, by a few other researchers and students. And for follow-up phases, then they have to really think about that. I mean, again, but if it's a throwaway program, and in some cases it's a throwaway program. I mean, you just want a little script in R or MATLAB or any other language in Python to just do certain analysis, visualization, and then you know that for no other paper in the future you're going to need it, then you can do it kind of in a patchwork and then hurry up way. But it's just like everything else. If you want something for a long run, then it has to be developed properly.
Thank you.
We have one more. Sorry, Stefan, did I cut you off?
I was just saying thanks.
There's another question on the notes. Would you like to ask directly to Vahid and David?
Yeah.
Yes, Matthew.
That was me. Just to dig it up. So academic software, particularly in existing projects, so it's not new ones, but ones that have been around for a while, there's often a tension between the sort of core development team of I work in computer science and predominantly with algorithm developers. So there's a tension between hey, I want to make cool new algorithm to build into this package. It's faster, it's clearer, all those sorts of reasons. And hey, my project has been successful. I have 1,000 downloads on CRAN. You know, people are using this. People are building tools on top of it. There's often a sort of really problematic tension between no, this is mine, and I make the decisions for me, and if anybody else wants to use it, then so be it, and the designing and sort of building out with end users in mind. And since both of you have worked on sort of a bunch of different projects, how exactly do you balance those two particular things, particularly if it's more than one individual working on the project, where you have people who are very ownership of the code and mindful of where they want to go, and those who are concerned about, so are we giving what potentially our end users, want as well? I hope that's sort of clear in terms of what I'm getting at.
No, I think that'd be a very interesting question. Vahid, I've gone first every time. Do you want to go first on this one?
You go ahead, please. You go ahead, and I will go afterwards.
Okay. So I think there's a number of aspects to it, and a really very interesting question, very live issue. I think we need to look at routes to impact being better refined, if that's the right word. So at the moment, I think we have a culture where you apply to research councils for funding, and again, the research is the output. So I would love to see it increasingly that the expectation is that your tools are released. The second thing is that I've built tools internally, and then there's been large pots of money available for commercialization of those. Yet when I spoke to the commercialization people and said, oh, I'd like a few weeks of my time to make an open source tool because it will have a prestige and impact, the silence was deafening. They wanted to see it turned into an actual commercial project. I think if we had more focus around this routes to impact, that you're able to evidence that one of the refable potentially, or one of certainly the esteem measures that you can use is how many people are using your tool and what's happening. I mean, I do think if you've written an R package and it goes on, or Perl or whatever, and goes on, I always get them confused, but it's CPAN, CTAN or whatever, and thousands of people are using that worldwide, that should be a reportable impact for you. It certainly would be if you were interviewing. If you come and interview with me privately as a developer and you say, oh, I've written this package and thousands of people are using it worldwide, that's a massive tick in the box. And I think it ought to be something that we're able to return and report on. The other side of that, which I think, if I answer the question correctly, is more about people than processes. People have this kind of very tight ownership of their code. I'm not sure how we can get the culture to change other than if we make it open access to code a requirement in the same way we make open access to papers a requirement. People do jealously guard their code and somehow think if they release it, A, people will steal it, B, people will do things to it, and C, they'll lose control. Of course, none of that is actually true. And I think in a general sense, and apologies if anyone here does this, but they're the kind of people that put copyright notices on their PowerPoint slides when they give a lecture because they're so worried that someone wants to steal their brilliant binary tree PowerPoint, which I don't think anyone does. But if we have that requirement as part of the funding brief and the ability to show impact through open sourcing of tool chains and how many people are using it, you would suddenly see a lot of crusty old professors sit up, and that would then go from the top down, to reference the earlier question, that they would then say, well, hang on a minute, yes, brilliant, we're getting papers out of this, but how are we going to tick this box about showing sustainability and impact?
Good. Perhaps I can also, answer a bit to Matthew's question. I guess, well, was a great insight by Dave, but my kind of understanding was that Matthew was asking, of course, the code ownership and the competition and the team dynamics, right? Of course, the whole thing of the dynamics and governance of a software project. I guess that's also a huge issue because it's like, who owns it? What's the pyramid architecture? Do we have a flat architecture or pyramid architecture? I mean, the whole
I'm working on open source R code. So just for context. So, but yeah, it's the flat hierarchy. It's the making decisions about going forward, project management sort of issues, because that's just a really big issue at its I've found.
Exactly, in the freelance community, right, in the free and libre open source. I mean, I've seen lots of papers. I've done some work on mining software repositories. I know Dave has done it, like looking at people have been mining the software repositories to make sense of how people work with each other. There are even research papers on that topic if you want. I mean, I'm not sure if you have seen them. People are doing research, to understand the team dynamics and even the, let's say, clashes or kind of the resistance in team members to different things. I mean, that's also a huge conversation by its own. Looking at even there's a workshop on that, human and cooperative aspects of software. Chase. So if you Google, that has been going on for more than 15 years, I would say. Looking at the team dynamics, governance, who does what, even open source, right? I mean, if you put a kind of suggestion forward or a patch request forward, how will it be seen by others? I mean, there's lots of human factors. There's a tremendous amount of human factors and non-technical things involved with it. But I just want to think. There have been some, methodological studies on that, but I'm not an expert on that, but just wanted to mention that. I would like to mention something about a slightly more technical. It's like you mentioned something behind your, in your comments mentioned about, you said if somebody has an idea of improving the performance of an algorithm, right? You said if you want to develop something and somewhere inside some of the functions that will make it faster or something, and then the guy would say, this already works and people are using it. Why should we make it faster? I mean, why should we touch it or change it? Well, I mean, of course, we can look at these things from non-technical or technical perspective. I mean, from technical perspective, I mean, again, it's like we have the software quality attributes, which is some of them are intrinsic, some of them are extrinsic. I mean, you say from outside that the software works, right? But if you want, improve the performance, you may want to improve the performance, improve the readability, maintainability, all the utility aspects. Most of those things are internal aspects, like internal quality aspects. So the end user will not know that if it's maintainable or not, of course, if he or she doesn't want to change the code or look at the code itself. But in open source, you will have other scientists that would most probably download it, would change any part of it that they wish, and they want to just make it customizable to their own needs or change the parameters or whatever algorithm is that. So I think that was what I wanted to mention. Then again, just to keep my answer short, is the team could come together and then prioritize the quality attributes to say which quality parts of this we want to improve. Because you cannot improve anything because you don't have enough time to improve everything. You will just need to prioritize, and that has to be usually made as a group setting if everybody agrees to each other.
Okay, Vahid and David, there are a few questions also on the document. Will it be possible for you to go over there at some point and address those? And also you mentioned quite a few resources in your answer, and I'm sorry I wasn't very good at recording that. It would be great if you can add those resources as well in the document. So we have to end this, and let's thank Vahid and David for their amazing workshop.
Thank you very much. Thanks for having us.